All right, let's talk a little bit about the mean value theorem. First, we'll start with a little bit of a concept overview, and then we'll do a particular problem. Okay, so here's the concept overview. I've got a xy plane here, all right, and here I've got any function, okay? But it can't be any function for the mean value theorem to work. In order for it to be a legitimate theorem that applies to the situation, you need to have three criteria. First off, you need to have a closed interval. All right, so the brackets here tell us we have a closed interval. On a graph, we would have closed circles. If it was an inequality, we would have inequality symbols that look like that. Okay, without that, if we have an open interval, then the mean value theorem doesn't apply. Okay, so that's criteria number one. You need a closed interval. Criteria number two, our function needs to be continuous. All right, so more or less what that means is that we can draw the function without picking up our pencil. All right, that's criteria number two. It's got to be continuous. And criteria number three, it also needs to be differentiable. All right, so that means everywhere I need to be able to draw a tangent line. All right, so in other words, if there are corners, if there are cusps, if there are sharp angles like that, we cannot use the mean value theorem. All right, so in this case, we need a smooth graph. Right, so often that's just what I'll say to summarize all that is we need a smooth curve, and we need endpoints that are included. All right, so what the mean value theorem says, so that was just the three criteria in order for it to apply. But this is what the mean value theorem actually says. It says the average rate of change is equal to the instantaneous rate of change in at least one point. All right, so the average rate of change, graphically what that is the slope of the secant line. All right, so from starting point to end point, that's the secant line. It's a straight line. And the slope of that should equal the slope of the tangent line in at least one point. All right, so in this case, the tangent line that has the same slope occurs, I don't know, I'm just kind of eyeballing, maybe right about there. All right, so in other words, the tangent line has to be parallel to the secant line, and it also probably occurs right about here. Okay, so the average rate of change, slope of the secant, has to equal the instantaneous rate of change, slope of the tangent. Okay, so graphically, that's what's going on in the mean value theorem, is that the average rate of change has to equal in at least one point the instantaneous rate of change. All right, so now let's do a particular problem. All right, so once again, problem number 9 from page 202. All right, so the first thing they ask us to do is find the equation of the secant line. All right, so remember when you're asked to find the equation of a line, you want to use the point slope formula. Now it's going to turn out we're not actually going to use it, but I want to remind you that that's generally the technique. I'll explain why we're not going to use that in a second. All right, so we want to find the secant line. So we need the slope, and we need at least one point. All right, to find the slope, we got to find both points. So let's do that. You need 2 points to calculate slope. So let's figure out the first point. So we want to evaluate our function at 0.5. So we're going to have 0.5 plus 1 over 0.5. All right, so 1 over means the reciprocal, right? So the reciprocal of 1/2 is 2. So that's going to be 2.5. All right, so that's 1 point. One of the points is 0.5 comma 2.5. Now let's figure out the other endpoint. So f of 2. So the x-coordinate's 2. Let's figure out what the y-coordinate is. 2 plus 1 over 2. All right, so hopefully you can see once again 2.5. All right, so hopefully now at this point you can see what I was talking about when I said we're not actually going to use this, right? Because this line is a totally horizontal line going from 0.5, 2.5 to 2, 2.5. So it's a totally horizontal line. You've heard me say this before, y lies, x flies. So a line that lies down is going to be a y equals line, and it's going to be 2.5. Okay, and what's the slope of this? 0. So if we did go through this point slope, we could. It would be y minus 2.5 equals slope of 0 times x minus, we could choose either one of these points. I'll choose 0.5. So 0 times anything is 0, and we add 2.5 to both sides, and we get y equals 2.5. But anyways, I know you could do all that, but I wanted to show you these steps in case it didn't work out in this particular case. All right, so our secant line has a slope of 0. So in other words, the average rate of change is 0. What the mean value theorem says is that the instantaneous rate of change for our actual function must be 0 in at least one spot. So what they want us to do now is find that spot. Okay, so our average rate of change here, slope of the tangent line is 0. So the average rate of change is 0. So now we got to figure out the instantaneous rate of change. Remember, whenever you want the instantaneous rate of change, you got to find the derivative, right? So let's calculate the derivative. And 1 over x is x to the negative first So we could think of that as 1 over x squared. All right, if you need some time to calculate this, break out a piece of paper, calculate that out, make sure that you can do that. Maybe you want to pause the video, but otherwise I'm going to keep on moving. Okay, so that's our derivative. Now we want to know where the tangent line has this slope. So f prime of x gives us the slope, right? So we want to know where the slope is 0. So we just calculate this out. So 1 over x squared equals 1. So x squared equals 1. So x could be 1 or x could be negative 1. Alright, so we want to consider both of these points except for the fact that our domain is limited, right? So we don't need to consider x equals negative 1. It is a critical point in this case because it makes the derivative equal 0, but it's not within our domain, so we don't have to worry about it in this problem. What we do want to worry about is x equals 1. So when x equals 1, the slope of the tangent line, instantaneous rate of change, is 0. Alright, so let's find the equation of that line. So we know the slope. The slope is 0, and we know the x-coordinate is 1, but let's figure out the y-coordinate. So f of 1 equals 1 plus 1 over 1, so that'll give us 2. Okay, so we're going to have a horizontal line that goes through the point 1, 2, and I'll save you some time here of going through all these steps, which are kind of unnecessary, and we know it's just going to be y equals 2. Alright, so that concludes the mean value theorem portion. I'm going to continue talking about some other things, but if all you need help on is the mean value theorem, you can kind of stop and write down any questions that you have and bring them to class. But I'm going to continue with the directions for numbers 15 through 22, the directions for those, but on this same problem. Okay, so if you're interested in that, keep watching. Alright, so now I'm going to continue with the directions for numbers 15 through 20. They ask us to find the extrema, and they ask us to find where the function is increasing and where the function is decreasing. Okay, so remember the extrema could happen in a few places, critical points or endpoints. Okay, so remember the critical points is where the derivative equals 0 or where the derivative is undefined. Alright, so here is our derivative. We already found it equal to 0 earlier. Remember we found that the derivative of x is equal to 0 when x equals 1, right? Remember we already did that? But then we can also recognize now that f of x is undefined when? Well, when x equals 0, right? Alright, so we want to consider that also as a critical point, except it's not in the domain, so we don't actually have to worry about that, right? Because x equals 0 is not in our domain, so we don't have to worry about that. And for that matter, x equals negative 1 was also a critical point, but we didn't have to worry about that because it wasn't in the domain. Okay, so the only critical point we need to worry about is x equals 1, but we do need to worry about these endpoints. Alright, so usually when we figure out where the function is increasing or decreasing, we'll make a sign chart. But we won't make a sign chart for the function, we'll make a sign chart for the derivative of the function. And we want to include all our critical points. So our endpoints, our critical points, and our other endpoint. Okay, so that's what we need to consider. And what we want to know is where our derivative is positive or negative. Because if we know where the derivative is positive or negative, we know where the original function is increasing or decreasing. Okay, so what we'll want to do is look at f prime of some point in between here. I'm going to do 3/4. So here's f prime, 1 minus 1 over 3/4 squared. 3/4 squared is 9/16, but we want the reciprocal of that is 16/9. So 1 minus 16/9, I can figure out what that actually is very easily, but all I really care about is the fact that that's negative. For a sign chart, all you care about is positive or negative. Okay, now let's figure out a point in between 1 or 2. So I'm going to do 1.5. Alright, so 1 minus 1 over 3 over 2 squared. 3 over 2 squared is 9/4. The reciprocal of that is 4/9. 1 minus 4/9 is 5/9, but all I really care about is that that is positive. Okay, so the sign chart tells me a lot. Since the derivative is negative in this region, we know our function is decreasing in that region. And since our derivative is positive here, we know our function is increasing in that region. Okay, so using our calculus, we can get a pretty good graph of what this is going to look like. First off, we can plot our points, 0.5, 2.5. So here's 0.5, here's 2.5. Then we have, well, I guess we never wrote it anywhere here, but when x equals 1, remember we got f of 1 to be 2, so we can plot that point. So there's 1, 2. And then we also have the point 2, 2.5. So that's maybe right there. Okay, so already we got 3 points. That was just plugging in numbers though. But now we can apply our sign chart, and we know that we're decreasing in between 0.5 and 1, and that's good because that means our graph is going to look like that. And then when x equals 1, our derivative is 0, so we should have a horizontal tangent here. And then we start to increase. So that's looking good. As always, it always feels good to check our work. So here is a graph on GeoGebra, and so we can see a lot of the points we were talking about. Remember, when x equals 1/2, we were supposed to be at 2.5. When x equals 2, we were supposed to be at 2.5. And when x equals 1, we were supposed to be at 2. So we're looking good, and we were decreasing in the region we said to be decreasing in, and then we were increasing in the region we said we'd be increasing in. And I just wanted to draw a few conclusions or connections between the graph of our function, which is the blue, sorry about that, and then the graph of our derivative, which is this dotted brownish red. Okay, so just a few connections. Remember, our derivative went from negative values to 0, then to positive values, right? So remember, we said that since the derivative went from negative to 0 to positive, then our function should go from decreasing to flat to increasing. And it does, right? And so whenever you see a derivative graph, you can look at this region right in here and know that our original function should have a minimum because we go from decreasing to 0 to increasing. So we should have a minimum. And vice versa over here, where we go from increasing to 0 to decreasing, or I guess I was talking about the original function there, the derivative goes from positive to 0 to negative, which means our original function should go from increasing to flat to negative, which means we're going to have a maximum. So when you see the derivative go from positive to negative, that means a maximum. And when you see the derivative go from negative to positive, that means a minimum. Okay, so I think we've beaten this problem to death. If you have any questions, please be sure to ask tomorrow. Thanks.